So you see there, in this particular problem, there are two ways of naming iron here. And okay, here. We have the normal way, which is just iron. And this is the charge on the iron, central metal. It's kind of weird because the metal is written first in the formula, like this. However, in the name, it's written last. Goes iron 3. Okay, so we have this complex, actually, which is tris ethylene diamine. We have to use the secondary numbering system, tris, because ethylene diamine has di in it already. And so that's why we use tris. And so that we don't split this up into two separate ligands, we wrap it in parentheses here. So tris ethylene diamine is going to be this. Can you tell what the coordination number of this complex is? 6. That's because ethylene diamine is bidentate ligand, and we have 3 of them. And so the coordination number is 6. There's going to be 6 bonds, chelating agent. Hexacyanido, that's going to take me time to do this new. I usually call it hexacyano, rather than hexacyanido. And so hexacyanido is going to have a coordination number of 6. And so we come up with this formula here for that. All right, so that's the one that we left off on, I think. Let's take a look. Oh, actually, the trisethylene diamine, let's draw that. So here I have a bis ethylene diamine here. And if you look at the ethylene diamines, they're opposed to one another here. I have one over here on this side. If I do a tris, I cannot connect these two. These two are in the axial position, and they're 180 degrees apart. They're too far from each other. So if I were to draw the structure of the tris ethylene diamine, iron 3 cation, it would look something like this. We'd put the iron here, and then we're going to have our 6 positions in an octahedral geometry. Now the ethylene diamines have to go in adjacent positions, so I can take the top one, and then any of these 4 will work. But I'm just going to take these 2. I'll put my E in there. Now, I can't go to opposite positions. So for example, if I try to connect this top one with the bottom one, it's too far. And so it only goes into adjacent here. So I'll pick another adjacent here. Again, it's too far to reach the opposing end. And so the last one will go here. Now the charge was given in the name. So this is iron 3+, and ethylene diamines are neutral. So this whole thing is going to carry a 3+ charge, or +3 charge. Here, this would be the charge, or the oxidation state on the metal. Yes, it's a bidentate ligand. There are 2 that you have to know. Ethylene diamine, and the other is oxalate, oxalato. The structure of oxalate?
The letters.
The formula?
The formula.
For oxalate? Yeah. Well, ethylene diamine is this. We have an NH2, CH2, CH2, NH2. And the NH2 has the lone pair that it can donate. And so the formula, if you wanted to write the formula for this, it'd be C2, H2468, H8, N2. This would be the general formula. We could also write a condensed structural formula, which would just be, NH2, CH2, CH2, NH2, something like that. The problem with writing formulas like this is there could potentially be isomers That is, same formula but different structure. Oxalate looks like two carboxylic acid groups stuck to each other, like this, back to back. And these would be called carboxylate groups because the acid proton has been plucked off and we're left with the anion. And so it's like acetate. But acetate would have two carbons. This only has one carbon. So this would be methanoate, two back-to-back methanoates is one way of thinking about this. And normally this formula is written C2O42-. In the name, you have to write it out. In the formula, we can abbreviate it. And so we could call this EN, or we could call this OX. But we'd never call this like tris N iron 3 because EN's the abbreviation. We'd have to write the whole thing out like they did up here. They would never use an abbreviation here for ethylene diamine. However, in the formula, we can use an abbreviation. Here. All right, these two oxygens would be the donor. Oxalato could never be a tetradentate here. And it wouldn't be these two oxygens over here. It has to be this oxygen here and this oxygen here. This oxygen up here wouldn't. For example, if we tried to pick these two oxygens here, what would the problem be? For bidentate.
There's no additional negative charge?
Well, the negative charge is better, that's for sure. And so that's a good point. You want the negative because that makes a better base. But there's another reason. It has to do with if these two oxygens bonded to the central metal, it would form what membered ring? You have to count the metal as one member of the ring. It would be form a four-membered ring. Yeah. Versus these two oxygens here would form a five-membered ring, which would be stable. And so there. Ethylene diamine has no problem. This is ethylene diamine. Propylene diamine's even less of a problem. Do you know what prop means? How many carbons prop is? Meth is 1. Yeah, Colin has it. F is 2. Prop is 3. So if we do propylene diamine, we're going to put a 3-carbon chain in here. And then we'll put the 2 amine groups here. Propylene diamine would make an excellent bidentate ligand. This would form a 6-membered ring and be very stable. What's after prop? Bute with 4 carbons. No problem there. Butylene diamines, no problem. How about methylene diamine? Methylene is how many carbons? 1 carbon. So we'd have 1 carbon in the chain here and then 2 amines. So this would be methylene diamine. Is methylene diamine going to be bidentate or monodentate? You say, is there a problem with methylene diamine here? Or does it look good to you guys? Yes. If it's bidentate, it's going to form a 4-membered ring, and that would be unstable. So this one actually turns out to be monodentate because of ring strength and not bidentate. So we see a pattern here. We can make predictions. You know, there are other things like this is back-to-back oxalates here, but we could have other structures that have back-to-back with some kind of chain in between. You know, this kind of thing, or we could have a mix. Like we might have a carboxylate group on one side and an amine group on the other side, as in amino acids. You know, amino acids have amine on one side and a carboxylic acid group on the other. So we deprotonate that, then we can have a bidentate ligand potentially. You know, there's a metal around. All right, so let's name these ones up here that we encountered earlier. I'm sorry? All right, this is what we call a complex anion. And so if we have an anion, there's something special we do to the metal. So for example, this is cobalt, and we figured out the oxidation state of the cobalt earlier. The oxidation state is based on adding these up. We know what chlorido is. Chlorido is a -1, and we have 4 of those. So 4 times -1 gives us -4. And then ammonia, or amine, is neutral. We have 2 of those. So 2 times 0 is 0. So -4 plus what gives us a net charge of -1? So we have 4 times -1 plus 2 times 0 plus 1 times x, yeah, is equal to -1. And that's correct, it's 3. So we know the charge on cobalt's got to be +3. And so we call it cobalt 3. But this is an anion complex. Whenever we have a complex anion, we have to change the name. Cobalt's not one of the special ones. You know, the special ones that we covered were argentate. Do you guys remember those? Argentate, orate, plumbium, plumbate, these ones. These ones get the special treatment. You can kind of tell from the symbol. So what we're going to do for this one is we're just going to add the 8 ending. So this is incorrect. It's not cobalt 3. We're going to call it cobaltate 3. Cobaltate, Roman numeral 3. But the metal doesn't go first. The metal goes first in the formula. The metal goes last in the name. And so we have to put the ligands first. But we have a problem now. We have chlorido versus amine. Which ligand should we name first? Should we do the amine first or the chlorido first? Amine. And so we're going to do it alphabetically based on the name. And so we have 2 amines. So do we use di or do we use bis? Di. Diamine. Do I use 2 M's or 1 M? 2 M's. Diamine. Ooh, I ran out of room here. Because this is all supposed to be one word. There's not supposed to be any spaces, but I screwed this up. So I'm going to have to insert it here. And what do I need to insert here? Yeah, so there should be no space. It's going to go ET, you know, from the mean to the tetra. And there's no space between tetra and chlorido. And there's no space between the O and the C of cobaltate. So it's diamine tetrachlorido cobaltate 3 ion. I can tell it's an anion because of the 8 ending here. For neutral, we don't have to mess with it. This is a neutral complex because we have X, which is cobalt. We have just one of those. And so that's 1X plus 3 minus 1s plus 3 zeros is equal to 0. And so the oxidation state on cobalt's got to be +3. So it's going to be a cobalt 3, not a cobaltate in this case. And so we have chloro and amine again, so this is not that. useful because it's just going to be a triamine. In this case, it's going to be a trichlorido. Cobalt or cobaltate. Cobalt. And do I need a space here between the cobalt and Roman numeral or no space? No space. Roman numeral 3. Since it's a neutral complex, that's the name of this whole thing. Triamine, trichlorido, cobalt 3. It's going to be a molecular compound. These are all covalent bonds.
Wait, why is it cobalt not cobalt?
Because it's neutral and positive, you leave the metal as is. For negative complexes, we change the ending to 8, and if it's one of the special ones, silver, what are the special ones here? Iron, is ferrate, copper cuprate, tin stannate, silver argentate, lead plumbate, gold borate. So we have to remember these. The ones with the funny formulas. All right. This one is a coordination compound, but it has a normal cation. And so this is like a regular ionic compound. And if this were regular, the cation's potassium. So do we say tetrapotassium or just potassium? Just potassium. That's good. And so this is potassium with 2 S's. And then here we need a space. We always need a space between the cation and the anion. So now we have to name the anion. So we name it the ligands first. So this would be hexacyanide, except we changed the ending on cyanide to cyanido. Yeah. Hexacyanido. Now, this whole complex is going to have what charge? Okay, so this is, it's got to be a -4 because we have 4 potassiums. And so each cyanide is -1. And so that means iron must be what oxidation state? +2. And so should I call it iron Roman numeral 2? Or should I call it ironate Roman numeral 2? Or should I call it ferrate Roman numeral 2? Ferrate. This is ferrate Roman numeral 2. And that thing is a 4- anion. All right, let's take a look at another example here, chapter 14. This time we're gonna go from the name to the formula. So we'll do a set of these. Oops, not chapter 14, chapter 24. We'll do these ones here. How about that? Oh, we already did these. We need to go from the formula to the name. Is that correct?
Yes.
All right. So we could do number 2 or number 3. Which one? Which one do you want to do? Yeah, all right, let's do 3. Okay, shoot. Let me insert it here. This one is a complex compound. So we have a complex cation here and just a regular anion. So the anion should be easy. This is just normal what? Yeah, is that chloride or chlorido? It's chloride. It's only chlorido if it's bonded to the central metal here. And so we just need to name the cation. So let's try to name the cation here. So do I start with silver, or do I start with argentate, or do I start with amine? Amine. Okay. So, and how many amines do I have? 2. So that gets diamine. 2 M's. Okay, is this going to be silver, silverate, argentate? Okay, this is a anion or cation or neutral. If it's cation or neutral, then we just leave the metal as is. If it's an anion, then we change it. The whole thing has to be an anion, not the metal. And so we're just going to leave it silver. The charge on silver. Well, ammonias are neutral, and chloride's -1. Therefore, silver must be +1. Silver only has 1 charge. We'd never do this for anything else. For example, we'd never call silver chloride, for example. Silver chloride is AgCl. It would be wrong to use the Roman numeral here. So we'd never call this silver 1 chloride. Why? Because there's only 1 charge on silver. And what is that charge? Is +1. But for complexes, we're going to do it. You know? So we wouldn't do this in a normal nomenclature. This is wrong. But we'll do it here. So it's going to be diamine silver 1 space chloride. Yeah. Complexes always state the charge of the metal, regardless. You know? And the reason is some complexes can actually have silver 0. That is, a neutral silver gets trapped in there. And a neutral silver atom can act as Lewis acid, accepting a lone pair. Don't we do the metal comes always first in the formula, but in the name, it's opposite. So, yeah, you always have to think opposite. All right, if we go on to B, B has a normal anion too. SO4 is called what? Sorry. SO4 is sulfate. What's the charge on sulfate? -2. So this whole complex must be +2. Okay, then we look at the ligands. Ammonia is neutral, water is neutral. That means copper must be +2. And so this whole complex. So we named the ligands first alphabetically. So what should go first, amine or aqua? Amine. And so how many amines do we have? 4. So that is tetra. Now, so for example, sometimes we get rid of the double vowels, sometimes we don't. Convention was we get rid of the double vowels, like carbon monoxide or carbon monoxide, which is correct? Monoxide. And so, but now we're going to retain them. I was just looking at the example here. And so your book retains it. So it'd be tetraamine rather than tetramine. And the amine is with 2 M's here. Okay, and then what? Space or no space? No space, diaqua. Copper or cuprate? Copper. Roman numeral 2. Space, sulfate. Okay. All right. When we have a neutral complex like this, oftentimes we will put the brackets here. The charge is just going to be 0. So most often the brackets are included in there. In this case, they omitted the brackets. We put the brackets in there to indicate that it is a complex. So what goes first, platinum, chlorine, or En? Chlorine. And so this would be what? Dichlorido. Then what? You need to know how to spell this one because we can't use the abbreviation here. You have to spell it out. And so how do you spell this next one? It's going to be E-T-H-Y-L-E-N-E. Ethylene. Okay, and then D-I-A-M with 2 M's or 1 M? 1 M. Diamine. Now, this might be confusing because this might look like we have 2 chloridos, 1 ethylene, and 2 amines. So there are two clues. One clue is I don't have 2 amines because this is not double M. In fact, I have an ethylene diamine. This whole thing comes together. So in this case, I'm going to put the parentheses there just to show that this is one ligand. So dichlorido, ethylene diamine, platinum or platinate? Platinum. And what's the charge on platinum? Plus 2. So Roman numeral 2. And the whole complex is a 0 charge, neutral.
In the name, you always put
Pretty much.
Does ethylene diamine have a charge?
Ethylene diamine's neutral. It has no charge.
I'm kind of confused. When do we put the O suffix on the original?
Only when they're anion ligands. If they're neutral, there's no O. And so chloride anion, so it's chlorido. Ethylene diamine, neutral, so you just leave the name. Unless it's one of the 4. The 4 are aqua, amine with 2 M's, carbonyl, and nitrosyl, or the other name they gave that.
Amine with 1 would be like NH2.
Yeah, it'd be an NH2 with one other bond to it, carbon. It doesn't have to be an NH2. It could be an N or an NH. So this is also amine. This is trimethylamine, and it behaves just like ammonia, although it's a bit bulkier because you have these big methyl groups compared to hydrogens. But this just looks and behaves like ammonia. And this has no N. If I got rid of one of the methyl groups and replaced it with a hydrogen, then it'd be an NH. And so the means are going to either be N, NH, or NH2. But the problem is, I think I already talked about this. How about trifluoro? Is this an amine? Should I call this trifluoroamine, like trimethylamine, or is this nitrogen trifluoride? This is nitrogen trifluoride. This is not an amine. Can you tell me why this is not an amine? No, the hydrogens don't play a role in the bonding. We're looking at the lone pair on nitrogen.
Oh, because and what it because the X on her they're not gonna give I remember you talking about this.
Yeah, you remember me talking about it, but the thing is that, the best time to review is like shortly after, not like right before the test. What was it? What was I saying? What was he saying? The night before the test.
Yeah.
The night before the test, if you were hit with this question on the exam, would you be able to cram it right before? So what you want to do is you just want to make sure you get it that way. What I do is I just review it, every day. So if I didn't really quite have this drilled into my memory, by the time the test came, I would, because I'd probably see it so many times. Every day. It's already, last week. So I've seen it multiple times. So what was the reason why nitrogen trifluoride is not amine? Well, it's still not very acidic. It's not a great. I mean, it's more acidic than this one for sure. But
Charge on the nitrogen, like loses to fluoride.
yes, yeah, it was a charge. I mean, you could do it very simple based on polarity. This nitrogen is delta minus, whereas this nitrogen is delta plus. And you can see this more dramatically with oxidation state. What's the oxidation state of the nitrogen in trimethylamine? Oxidation state is winner take all. So if nitrogen takes all the electron, winner being more electronegative, nitrogen is more electronegative. If nitrogen takes all the electrons, how many does it end up with? 8. How many valence electrons does nitrogen normally have? 5. So it's 3 extra electrons, so it's minus 3 for 3 extra electrons. That's what we call electron rich, because do you remember we looked at the range of oxidation states for nitrogen? What was the range?
-4 to +4.
That was for carbon. -3 to +5. And so this is another benefit of, I usually, there's a lot of like little things you either memorize or you can look at the periodic table. If I pull down the periodic table, it might be easier to see. -3 comes from nitrogen wanting an octet. So it needs to get 3 extra electrons. +5 means, it loses 5 electrons to be like helium. So we look at going to the nearest noble gas. For nitrogen, it would be neon, gaining 3 electrons, or helium, losing 5. And so this is on the electron-rich side, which is good, because if you're an electron pair donor, you should be rich with electrons, right? What's the oxidation state of nitrogen here? +3. Fluorine is going to be the winner, leaving nitrogen only this lone pair. And so it's lost 3 electrons, so it's +3. So this is on the poor side. It's not maxed out poor. I mean, it still has these 2 electrons it could lose, bringing it to +5, but it hasn't. And so this is not an amine here. Yeah, basically, it should be delta minus. What defines amine is it has a nitrogen with lone pair it's willing to donate. This nitrogen is not willing to donate that lone pair. It has a lone pair, but it's not really willing to donate, because if it donates, it's going to lose one of them.
Yeah. So it's kind of like that when I said acidic. If I said that, I'm like a test. Would that be wrong?
Well, the acidic, oops, um, not entirely. Acidic means it has to accept a lone pair. And so how is this nitrogen going to accept a lone pair mechanistically? And mechanistically means with the arrows. It's not easy. If this nitrogen accepts a lone pair, what happens to one of the fluorines? It has to leave as a fluoride. And so it depends if it's willing to leave as a fluoride versus if it's unwilling to leave as a fluoride, you know. And so um, acidity for nitrogen becomes a little bit more tricky. Whereas other cases, we just push the electrons. So for example, if we had a double bond, we can just kick the pi bonding electrons out. And it's a lot easier mechanistically. It's not to say it doesn't happen, you know, it could happen, no problem, you know, and it does happen, but it's not just a simple matter of it's going to be a bit more complicated. And so that's why I didn't. Well, what I'm talking about there is nitrogen cannot exceed an octet. And so if it accepts another pair of electrons, something has to give, you know, something is going to get kicked out. All right, going to this next complex, we have a complex cation here, a 2+ cation. And so what do we name first? Chromium, bromine, or water? Water, because we call it, this is alphabetical, we don't call it water, we call it aqua. And so it's A for aqua, not W for water. How many of these do we have? 5. 5 is penta. Now, should we call it pentaqua or pentaaqua? Well, yeah, your book is going to do pentaaqua. Pentaaqua, and then we have bromide, but it's not called bromide, it's called bromido. This is an anion, and anions get the O ending. So -1. And then is this going to be chromium or chromate? Chromium. Now we have to figure out what is the charge on chromium. +3. So we're going to have Roman numeral 3 here. This is an ion, so we could write ion there. Or we could leave it off and you could figure out if it's an ion or not. Certain things you have to write ion. In this case, we don't have to write ion because if we write out the formula for this, obviously it's going to have a charge. Things that we have to write ion for are like sodium. You know, sodium versus sodium ion, 2 totally different things. Okay, this is an ionic compound here. The cation, do you recognize that cation? Rubidium. Monorubidium or just rubidium? Just rubidium. All right, now we have an anion. So do we do silver or fluorine first? Fluorine. So this is going to be called tetrafluorido. Fluoride, FLO or FLU? FLU. ORID. Fluoride or fluorido? Fluorido. Silver or, what's the Latin for this? Argentate. Silver or argentate? Argentate's correct. Why? Because it's an anion. Rubidium's a cation +1. So this whole thing must have what charge? -1. So this is going to be argentate. What's the charge on argentate? 3. There's something wrong with this, but it's all right. We'll just name it. What's wrong with this is this charge on silver is exceptionally high. In fact, it wouldn't be very stable at all. And so I think they made a mistake. And do you know there's one other reason I think they made a mistake, and that is, do you know what the coordination number for silver is? You might not know. Once in a while we go through these tables and we look for patterns. Yes, your guess is correct. What is the coordination number of silver? It's 2. Is it 2N4 or just 2? It's just 2. Here's an example of it right here. So either that's very unusual, complex, or it's wrong. I think it's a typo. I think it should have been not tetra, it should have been di. Then it makes sense. Coordination number is 2, and the charge on silver is +1. So there are other errors in this book, and so that's always a tricky thing, to deal with, because if there's an error in the book, it screws things up. But based on what we know about the coordination number and charge on silver, I'm confident that this is a typo and not some unusual species. All right, let's go to the next one. The cation's easy. Is that disodium or sodium? It's just sodium. Space, and then the anion. Iron, cyanide, or NO. What was the NO called? That's called nitrogen monoxide, but we don't use its normal name, nitrogen monoxide. We call it oxidonitrogen. Oxidonitrogen, yep. What a funky name. Or nitrosyl. I much prefer nitrosyl, but we'll try oxidonitrogen to be consistent with the book. All right, so which one do we go first? Cyanide, okay, versus oxidonitrogen. And so we have 5, that's penta. Cyanide or cyanido? Cyanido. And then this is all one word, oxidonitrogen. If you call it nitrosyl, that's fine. Pentacyanido, oxidonitrogen. We probably should put this in parentheses, because nitrogen, the molecule nitrogen, can be a ligand. Did you know that? It can donate, potentially. Would it be a bidentate ligand or monodentate ligand? Bi? Mono? Yeah. This could be a monodentate ligand. And so to prevent confusion here, because we could have an oxide ligand, or we wouldn't call it oxide, we call it oxido. We have an oxido ligand and a nitrogen ligand, the neutral nitrogen molecule. To prevent that confusion, we're going to put this in parentheses here because that whole thing is oxido nitrogen. Another reason I don't like this name. One of the very common ligands is this. Oxygen. Oxygen is a ligand, and there are a lot of complexes in biology. And for example, hemoglobin is a complex. Hemoglobin has iron 2 as a central metal, and it's a coordination number 6. And have you seen hemoglobin? Let's show you hemoglobin here. Actually, our book. Maybe I'll just get the one from our book. This is hemoglobin. Well, this is part of hemoglobin here. Do you see in the center here this brown one? This brown one is iron 2 stuck in the center. It's got a coordination number 6 in this distorted octahedral configuration. Do you see this top ligand? It's black and red. Do you know what black and red is? Carbon and oxygen. Do you know what this molecule is? Carbon monoxide. Carbon monoxide is an excellent ligand. It's a great Lewis base. And it's a better ligand than oxygen. And what happens is oxygen likes to bind to it. It binds weakly. It doesn't form that strong of a coordinate covalent bond. It's what we call labile ligand. Labile ligands are weakly bonded. And then we have inert ligands. Cyanide would be like an inert ligand. Once it binds, it's stuck on there. It's inert. It doesn't really break off easily. It's like the chelating agents. They're hard to break off. It's pretty inert. Whereas oxygen is labile ligand, which is good. You want oxygen to be a labile ligand because hemoglobin transports oxygen molecules. And so they got to be able to attach and break off. But if a cyanide gets in there, the cyanide binds to the central metal and doesn't allow oxygen to go there. It's not a triple bond, it's a single bond. Here, the triple bond doesn't bond. The triple bond is the carbon and oxygen part.
Does it take it off by the carbon?
Yes, so it would look something like this. If we look at the carbon monoxide ligand, so let's say we have the iron 2 plus here, and in hemoglobin, it's bonded to a bunch of other stuff, here. And carbon monoxide is like this. Carbon monoxide has an interesting charge. What's the formal charge on carbon and oxygen? Yep. This is very weird because, why? Yeah, oxygen's stronger, so it should be oxygen, not losing an electron. But in this case, oxygen ends up with 5 electrons. Carbon ends up with 5 electrons. So oxygen loses 1, carbon gains 1, which is weird because oxygen is much more electronegative. But what overrides that? The octet. We could have zero formal charges, no problem in this. But what this makes is a carbon with a negative charge. Whenever we have a carbon with a lone pair, it's got a negative charge, and that makes it a powerful Lewis base. And so any carbon with a lone pair is a powerful Lewis base. And it's going to be the carbon that's going to donate. Would this oxygen be a good donor with a positive formal charge? No. No. Bases are negative. We want negative. Acids are positive. So, Colin, you're right in the sense that acids are always positive. And so the more positive, the better the acid. But there are other factors that you got to consider here. So even though this oxygen is positive, I may or may not consider that very acidic. Maybe it's pretty acidic. Something can attack, and then we break one of the pi bonds. That should be fine. Okay. So nitrogen, like this molecule, can be a donor. One of the nitrogens can donate a lone pair. So to prevent confusion there, again, we put this in parentheses. And then is it going to be iron or ferrate or ironate? It's going to be ferrate. So it's got to be a negatively charged complex. And so what is the charge on this complex? Well, we can tell by how many sodiums we have. We have 2 sodiums. That means this complex must be -2. If this complex is -2, then iron must be what charge? +3. So +3 -5 is -2, +0 is -2. Oxidonitrogen is neutral, or nitrosyl. So this would be pentacyanide, oxidonitrogen, ferrate 3, or using the old nomenclature system pre-2005, this is called pentacyano nitrosyl ferrate 3. All right, so those are some examples of nomenclature. We want to know nomenclature and a little bit about structure. You don't have to be able to predict what the structure is or what the coordination number is, but you should be able to figure out what the coordination number is. When we have a coordination number of 4, it gets tricky because a coordination number of 4 means it could be either tetrahedral or square planar. And we can't use Vespert to determine which it is because Vespert fails. In fact, a valence bond theory fails. We have to use molecular orbital theory for this, the full quantum mechanic version. Iron's positive, but the complex is negative. Yeah.
So it's in the complex that's negative.
Yeah. Yeah. The same thing with silver here. Silver is positive, but the whole complex is. This should be really E. Let's correct E. E should be this. AgF2. Then it makes sense. And so this would just be rubidium, difluorido, argentate, because the complex is negative. This complex would be -1 because rubidium is a positive one. And the silver would be what charge? This would be Roman numeral 1. It's an error. All right, so those are some, and then I did a chunk of the homework for this because we went through those.
Wait, when is our first test?
Next week. Next week we're going to have our test. And the test is going to consist of nomenclature and reactions, I think. So we should try to take care of some of the reactions. So you're, Isaac, you're going to have to log on to Canvas, and I have it posted there, including the syllabus, and links to the videos are there as well. But we'll just take a break right now, and then we'll start the lab. The lab is a dry lab. We're not going to do any wet reactions, wet chemistry, they call it. So, resume this. So, I'm gonna go ahead and download this here. See the downloads. All right, so let's take a look at number 2. Number 2 is a bit tricky. This is very similar to what we were looking at earlier, but sometimes it could be advanced. Like this one looks deceptively simple, maybe, but it isn't so simple. And number 1 we already did in class. So, solid potassium sulfide and sodium chloride solution are mixed. And so, what was the formula for potassium sulfide? You guys got K2S is correct. That's good. And it's solid, so we'll write solid here. And then it's aqueous sodium chloride or sodium chloride solution, which would be NaCl, sodium chloride. Now, when you put solid potassium sulfide into a solution, will it dissolve? Yeah, potassium salts are all soluble, so this is going to dissolve. And so the first thing is the K2S dissolves. And so let me write this here. The K2S solid, when it encounters the solution, will form K2S aqueous. Now, the next step here is, so I look at, is it soluble? The next step I look at is what happens. Is it a strong electrolyte? It's a strong electrolyte. So it should dissociate into 2 potassiums and 1 sulfide. And so the first thing we look at is solubility. It's a soluble salt. The next thing we look at is electrolyte properties. And soluble salts are strong electrolytes. But you should know something about this. You usually memorize the 7 common strong acids, or have a pretty good idea of what they are. But do you have the strong bases memorized? Like what? Hydroxide. Okay, so let me ask you this: sodium hydroxide, strong base? Yes or no? Yes. But when I look at sodium hydroxide, often I think of a soluble salt. The sodium salts are all soluble, so soluble salt, also strong base. And so one of the things we might think is strong bases also dissociate 100%. Is that correct? But I separate it differently. I think of sodium hydroxide as being a soluble salt, and soluble salts dissociate. And so, it's dissociated into sodium ions and hydroxide ions. And then I think of hydroxide as being the strong base. This is the strong base. What if I had something like magnesium hydroxide? Would you expect magnesium hydroxide to be twice as strong because it's got twice as much hydroxide? No. In fact, magnesium hydroxide we don't consider a strong base. Not a strong base. Why? It doesn't dissociate. It's an insoluble solid. And so it stays together. We classify it as insoluble. Some will dissolve. So sodium hydroxide, one of the uses for sodium hydroxide is drain cleaner. It's called lye. Magnesium hydroxide is used for different things. One application is milk of magnesia. Milk of magnesia is a suspension. So it's a pasty, so it's like chalk suspended in water. But people consume this, so it's all right. So when I think of the strong bases, I think the most common strong base are the soluble hydroxides. What are the soluble hydroxides? Group 1, ammonium, and not group 2, just calcium, strontium, barium. And so when we have the strong bases, these are the strong bases I have memorized. The soluble hydroxides, so potassium hydroxide, sodium hydroxide, cesium hydroxide, calcium, strontium, barium hydroxides, all those. These are going to yield a lot of hydroxide in water. What else? Do you have any other strong bases memorized? Oxides. The soluble oxides. Which would primarily be group 1 and ammonium, although ammonium might not be. Essentially, we don't have that as a rule, but oxides are less soluble than sulfides. Those are going to yield oxide. What else? The amides, right. The amides are in general soluble, so I don't really have to say soluble. The amides are just soluble. What else? Yeah, the soluble sulfides. Etc. But these are the main ones. Now, what you have to know is what is the strongest base that can exist in water? Hydroxide. This is the strongest base that can exist in water. What happens if we have a stronger base than hydroxide?
In water, there's the leveling effect.
Yeah, there's a leveling effect, exactly. All these bases are too strong to exist in water. And what happens with these bases that are too strong to exist in water is they hydrolyze completely. So strong bases are strong electrolytes. They're strong electrolytes. And electrolytes hydrolyze or ionize completely. But for bases, strong electrolytes, these don't ionize. These hydrolyze completely. So let's write that here. And this is kind of the leveling effect for the bases. And so what we observe is oxide is too strong to exist in water. It reacts completely with water to form two hydroxides. Amide is too strong to exist in water. And so amide plucks a proton off water to form ammonia and hydroxide. Sulfide is too strong to exist in water, so plucks a proton off to form what? These are all Bronsted acid-base reactions. HS minus and hydroxide. So this is the leveling effect. They all form hydroxide. And so we treat them all kind of as equivalent in water. Yeah. You could call HS minus bisulfide. It's no problem. So this is why when I look at this, I look at K2S. K2S is a soluble salt. It's a soluble salt. And then what I produce here is sulfide. When I look at sulfide, sulfide is a strong base. Now, do strong bases ionize? That is, break apart into ions? Well, what's sulfide going to break apart into? It's already an ion. So what do strong bases do? Strong bases don't ionize. Strong bases hydrolyze. So when I see this, this can't exist in water. Can't exist in water. Unless it's hydroxide. It's the only base that can exist in water. And so the first thing I immediately see is that this is not going to stay sulfide. It's going to be converted into bisulfide and hydroxide. Let me write that down here. So the first reaction that I see is going to be a very favorable reaction. Strong base hydrolyzes water completely to form bisulfide. What's the charge on bisulfide? It's got that wrong. -1. H is +1, sulfide's -2, and hydroxide. All right, so the driving force for this reaction is going from a stronger base to a weaker base. You know, sulfide is too strong, and so we're going to form the weaker base, hydroxide. This is the driving force for this leveling effect. The same can be said for the acids. That means water has to be a stronger acid than HS minus. This has to be a weaker acid. It's going to go that way. We can look this up on the acid chart as well. The acid chart would show us that this is what we expect. In fact, let me see if I can pull up the acid chart. The acid chart is also on Canvas. And so let me grab the acid chart here. It's under the chemical reactions link here, the redox acid base chart. So in this case, we can see we're going from sulfide here to hydroxide. So we're going downhill. Downhill is actually up on the right side and down on the left side. So this is downhill. That's what we want. We want to go downhill. Also for water versus HS minus, that's also downhill. So we're going from stronger acid, water, to weaker acid, HS minus, downhill. Here. And so those are the driving forces. So this is the first reaction that we see. It's going to be between sulfide and water. Okay, what else do we have? Let's say, okay, so this would maybe step 1 here. Is there some other step 2? And so what we had was we have potassium ions, sulfide ions. Oh, actually, we don't have sulfide anymore. The sulfide is going to react. So we're going to have HS minus, OH minus. And what else are we reacting with this? Sodium chloride. So sodium chloride is a soluble salt, so that's going to form sodium ions and chloride ions. So the first thing I'm going to do is I'm going to look and see if there's a potential metathesis reaction. And so I look for a precipitate. So potassium ions and bisulfide, do you think those will precipitate? No, all group 1 salts are soluble. Sodium won't precipitate with anything either. So metathesis, there's no precipitate. Is there a gas? No gas, unless we have H2S. If we had H2S, it'd be okay, but we only have HS minus. It's not a gas. And are we going from stronger to weaker? And so SA to AA, WA. Stronger to weaker acid? Yes or no? Well, what's the strongest acid present? The strongest acid present will be this, HS minus. And what's the strongest base? OH minus. But if we look at this reaction here, look at the reverse reaction. If we look at the reverse reaction, it's between HS minus and OH minus. What does that form? Sulfide and water. Is that going uphill or downhill? Uphill. So no, that's uphill. So there's no metathesis. The next thing we look for is redox. And what we want to do is we want to look. This is Bronsted acid base here. If we have Bronsted, I'm not going to look at Lewis. I'll just do Bronsted. And then we go to redox. And we look at the reactivity of these things. So in terms of potassium ions, are potassium ions very reactive? And the answer is no. Potassium ions are about the least reactive. They're down here at the bottom, second from the bottom. But they're an oxidizer, so we'll go ahead and write that in here. It's not very reactive, but it is an oxidizer. And so potassium ions are an oxidizing agent, but the second worst oxidizing agent on the chart, so it's pretty unreactive. And then we have HS minus. HS minus is not on the chart. It's not on here. So what that means is it's totally unreactive, or they just ran out of room. And so let's take a look at what you would expect HS minus to be. Would you expect HS minus to be electron rich or electron poor?
Electron rich because it has a negative charge.
Okay, we don't look at the negative charge here. We only look at the oxidation state. The reason is like nitrate. Would you consider nitrate electron rich because it has a negative charge, or electron poor because the nitrogen has a +5 oxidation state? What would you? It's electron poor because nitrogen has a +5 oxidation state. It's very poor. And so we don't look at the net charge. What's the oxidation state on hydrogen? +1, but +1's fine. That's the same as water. What's the oxidation state on sulfide or sulfur? -2. Now, oxygen forms oxide. Oxide, would you consider that electron rich or just happy as is? Happy as is. Sulfide's the same, so would you consider sulfide happy as is or rich? Actually, I consider sulfide rich. The reason I consider sulfide rich is because of its size. Is sulfide bigger or smaller than oxide? Bigger. So sulfide's bigger and has 2 electrons. Those 2 electrons are much easier to pluck off by an oxidizer. Does that make sense? Versus oxide's much smaller. So sulfide's much more reactive. And so in general, sulfides are pretty decent reducing agents. And so I'd expect this to be a reducing agent. It's not on the chart, but I'd expect it to be a reducing agent. But you'd need a pretty decent oxidizer. Do you think potassium ions are strong enough to oxidize hydrogen sulfide? No, not at all. Hydroxide I consider happy as is, you know. Do you think that oxygen wants to lose any electrons? No. This is happy as is, but if you're forced to make it, you might say it's a reducing agent, but this is fairly happy as is. But if we're forced, maybe it's a reducing. Maybe it's an oxidizer because of the H+. But it's kind of like water. Sodium ions are an oxidizer, but they're very weak. And chloride ions are reducer, but they're very weak. And so reducing agent Ra, oxidizing agent OA. All these are very unreactive. HS- would probably be the most reactive out of all these. Likely most reactive. But we don't have any decent oxidizers. The only other oxidizer present is water. Is water a very good oxidizer? No. Is it a very good reducer? No. Although it could go both ways. Same thing with hydroxide. Hydroxide could go both ways. It could be a reducing agent, lose, or it can be an oxidizing agent, gain, but it's pretty weak like water. And so likely there's no redox. In fact, there's no redox here. No redox. Everything's too weak. Well, you're looking for a stronger one. So once in a while, what you want to do is you want to go through the chart and look at the strong. What are the reactive species? And those are going to cause reaction. Right? The strong reducers down here and the strong oxidizers up here on the left. So we only have one reaction here, and that was the Bronsted acid-base reaction here. All right, let's do another example. Yes, and I would only do it if it's a double replacement. I would do it for single replacement too. It depends if you use single replacement, if you know. I don't. Let's talk about number 4 and number 5. You can do single replacement if you want, but you need to know something about these. Number 4 and number 5. All right, let's look at the next one, which was chlorine and sodium iodide. What's the formula for chlorine? Cl minus or Cl2 or Cl? And sodium iodide? NaI. So this looks like the A plus Bx, but it's not. That's wrong. You know what pattern this is? This is the X2 plus AY pattern. Do you know that pattern? This is another single replacement pattern. You don't have to know it. We don't need to know these patterns because we're going to use the what method for this. Well, we aren't going to do metathesis because chlorine is molecular and it doesn't hydrolyze. So we don't expect it, or it doesn't hydrolyze to any significant extent. So we don't expect it. Chlorine does react with water, but it's a redox reaction. Yeah. So what we're going to do with this one is we'll try redox. I want to try redox because chlorine is a strong oxidizer. And so I want to try redox. And if I do redox, I'm going to use the chart method. And so I'm going to inventory. Chlorine is not a strong electrolyte. However, sodium iodide is. It's a soluble salt, so it's sodium ions and iodide ions. And then I have one other species present. What's the one other species that's present here? Water. Sometimes the solvent can react. Then I consult the chart. Let's see. I gave copies of the chart last time. I have to bring an extra chart. We look at it. Chlorine is an oxidizer. Is it also a reducer? No, it doesn't occur on the right side, only on the left side. Sodium is only on the left side, so it's an oxidizer. Iodide is on the right side, so that's a reducer. Water is on both sides, so it's an oxidizer and a reducer. And then we look for the strongest oxidizer. Can you tell which one's the strongest? Chlorine, sodium ions, or water? Definitely chlorine. I don't think we need the chart for that. Sodium ions and water are pretty unreactive as far as redox goes. We look at the reducing agents. What's easier to oxidize, iodide or water? Iodide. We can look at the chart for that. We're uncertain. So the reaction should be between chlorine and iodide. And so I just copy the half reactions. So for chlorine, it's chlorine plus 2 electrons yields 2 chlorides. And for iodide, I have to reverse it. And so I'm going to go 2 iodides goes to iodine plus 2 electrons. And the reason is because these are my reactants. My reactants are chlorine and iodide. And so iodide, I have to flip from the right side to the left side in order to make it a reactant. In this particular equation, it's the 2 electrons here cancel the 2 electrons here. So 2 electrons on the right get canceled out by 2 electrons on the left, basically. And then we can combine these 2 equations. When we combine the 2 equations, we're going to end up with chlorine plus 2 iodides yields 2 chlorides plus iodine. And then we look for driving force. So the chlorine we had labeled, that's our oxidizer. Iodide we labeled as a reducer. And then we use the half reactions. You know, the conjugate reducer of chlorine is chloride. So that would be the reducer. And the conjugate oxidizer of iodide would be iodine. So this would be the oxidizer. And so we have our oxidizer in the forward, our reducer in the forward, and then we compare that with the reverse. Okay, then we see which way is downhill. So going from chlorine to iodine or iodine to chlorine, which way would be downhill? Chlorine to iodine. That's correct. So up here we have our chlorine, and then we're dropping down to iodine way here at the bottom. So chlorine to iodine downhill. So we have driving force here. We're going from stronger to weaker. That's our driving force. If this is correct, then the reducing agents have to be the same. We can verify that as well. And so in this particular case, we're left with the net ionic equation. And so when we use the chart method, we end up with the net ionic equation. We don't have to do the ionic and the complete. This is NIE. So we have reaction there. I wouldn't expect any acid base. The only acid base would be water. Iodide's too weak. And sodium ions, nothing. And as I said before, there's no metathesis because chlorine doesn't consist of ions. Okay, let's look at the next one, and we'll do that one, and then let you guys work on these. Next one would be sodium is carefully added to aqueous potassium bromide. No, maybe we should do number 3. We'll do number 3 after we do number 5. So let me do number 5 first, and then we'll come back to number 3. What was number 5? Sodium is added to aqueous potassium bromide?
Yeah.
Okay. What's the formula for sodium? Na or Na plus? Na solid. It's a metal. Metals are solid. We don't call it, sodium is natrium. But we don't form too many complexes with sodium, so I'm not going to worry about it. Plus aqueous potassium bromide. KBr. Okay, so this looks like ABX. Should I go ahead and do an ABX? ABX, single replacement? Yeah, we could do that. This is going to form AX plus B. Sodium bromide and potassium. And then we compare sodium versus potassium on the activity series. We have the upside down activity series on our chart. Here. So you recall lithium is the most active, and then potassium is the second most active, and sodium would be the fourth most active. So we're comparing sodium and potassium. Potassium is more active than sodium. And potassium is more active than sodium. So we're going from less active to more active. Is that uphill or downhill? This is uphill. And so the driving force would be the reverse. More active to less active. So we expect NR reaction. But I should say no reaction for single replacement. For this single replacement. But it turns out no reaction is wrong. And so if you don't want to memorize all the exceptions, then the best thing to do is use the chart method. That way you don't have to memorize these exceptions. What was the exception in this particular case? The reason we got it wrong is because we ignored water. And so we have sodium solid, potassium ions, bromide ions, and water. You might have known that the alkali metals react violently with water. And there are a lot of videos on this. And so sodium ion is very unreactive. However, sodium metal is extremely reactive. This is a powerful reducing agent. Potassium ions are extremely weak oxidizing agent, second weakest on the chart. Bromide is a pretty decent reducing agent. Water is both an oxidizing agent and a reducing agent. So it turns out the strongest reducing agent is sodium. Sodium is a powerful reducing agent. And the strongest oxidizing agent on the chart is water. Here. Water versus potassium ions. We can see that water is a bit tricky because water doesn't belong here at the bottom. As far as oxidizing ability goes, where's water ranked? Yeah, between zinc and aluminum ions, right here at the 3 dots. So water goes there, which means water is more powerful than potassium ions. Potassium ions is second worst. Water is up at 1, 2, 3, 4, 5, 6, 7 in the 7th position, 7th worst on the chart. Water is pretty bad, but it's not the worst. But it's the best we got. And so if water is the best we got, that's all we have. And so what we're going to do is sodium. What can happen to solid sodium? It can go to sodium ion plus an electron. So we just copy this off the chart. This is backwards, so I had to reverse it. I had to reverse it because I don't have sodium ion, I have sodium metal. And so I flipped it from the chart. If you recall what the chart showed sodium ion plus an electron goes to sodium metal. But I don't have sodium ion, I have sodium metal, so I flipped this reaction backwards from the chart and wrote it here. So sodium metal goes to sodium ion plus an electron. Well, that takes care of the sodium metal here. And water, I can just copy off the chart. And so if I look at water, I have 2 waters plus 2 electrons goes to H2 plus 2 hydroxides. So this one I just copy right off the chart. And so 2 waters plus 2 electrons goes to H2 gas plus 2 hydroxides. All right, and then I have my water here. So I have my sodium and my water. That's what's reacting. This would be the most likely reaction to occur, but we need to look at the driving force, if there's a driving force or not. The electrons don't balance, though. Over here I have 2 electrons. On the left, I have 1 electron on the right. So what I need to do is need to make these balance. So I'm going to multiply the top one by 2. And now they cancel. 2 electrons on the left cancel the 2 electrons on the right. And then I'll combine the 2 half reactions. So I'm going to get 2 sodium solids plus 2 H2O liquids. This is going to yield 2 sodium ions plus H2 gas plus 2 hydroxides. Okay, then I'm going to use the conjugate relationship. So sodium was my reducing agent, therefore its conjugate oxidizer will be sodium ions. Water was our reducing agent, therefore its conjugate oxidizer will be hydrogen and hydroxide. Or this is, sorry, this is not reducing, this is an oxidizing agent. So its conjugate reducing agent will be hydrogen and hydroxide. And so sodium is a reducing agent, water is our oxidizing agent going forward. Going backwards, sodium ion will be our oxidizing agent, and hydrogen and hydroxide will be our reducing agent. And then we'll just look at the oxidizing agents and see, are we going downhill or uphill? So we're going from water to sodium ion. Is that uphill or downhill? So water is here between zinc ion and aluminum. We place that here based on the number over here on the right. It's minus 0.828, and that fits right in here. And then we're going to, from water, we're going to sodium ion. So sodium ion, that's downhill. So going from water to sodium ion, that's favorable downhill. So that means we're going from stronger oxidizer to weaker oxidizer here. And so that would be driving force. If I did this correctly, then this must be a stronger reducing agent, sodium, than hydrogen and hydroxide. And so this is the reaction. We expect reaction to occur. And so this one is something we'd miss if we just went ahead and blindly used the single replacement form, which appears to fit here. All right, we'll take a look at the other one. What was the other reaction? All right, I'm sorry, what was it again? The first one? Iron 3 sulfate. Okay, sulfate is a 2, so I'll cross multiply here. And iron 3, so it should be Fe2SO4 3. It's a solution. Sulfates are soluble except for silver, lead, mercury, calcium, strontium, barium. So this is soluble, so that's aqueous. You can leave off the aqueous. If you leave it off for all of them. If you put it on for all of them. So I'm going to just leave it off. If I leave it off, then that means it's aqueous. If this were solid, I'd write S, but it's not. Plus aqueous ammonia. Aqueous ammonia participates in metathesis reactions. Strong bases hydrolyze water completely. However, weak bases weakly hydrolyze. So weak bases don't weakly ionize. Weak bases weakly hydrolyze. But what that means is we're going to take ammonia and water, and we're going to make a little bit of ammonium and hydroxide. And so remember, it's greater than 99% over here and less than 1% over here. But that less than 1%, actually it's less than 0.1%, is enough for metathesis. Ammonium ions aren't very reactive in metathesis reactions. Why? In fact, when I think about metathesis ammonium, I think unreactive, pretty much. And that's because ammonium salts are all soluble, so we're not going to form any precipitate. So, however, hydroxide, I think, is very reactive because hydroxide reacts with all metal cations. Hydroxide reacts with all metal cations except for which ones? Yeah, group 1, ammonium and calcium, strontium, barium. All the other metal cations, hydroxide reacts with. So hydroxide loves metal cations. That's one of the chemical properties of hydroxide. Except group 1, ammonium and calcium, strontium, barium. So when I have ammonia, what I do is I just go ahead and add water. And when I have ammonia and water, I treat this as if it were ammonium hydroxide. But, there's only a tiny bit of ammonium hydroxide in there. And when we write equations, we write the major species. Like this. And so what that does is it turns this into an AB plus CD pattern. And so this is metathesis. Now, why don't I just replace ammonia and water with ammonium hydroxide? Because it's ammonium hydroxide that's reacting, and that's correct. It is ammonium hydroxide. So some instructors will have you replace ammonia and water with ammonium hydroxide. It's like carbonic acid. You got to replace carbonic acid with water and CO2, but here I'm not. Do you know why? The reason I'm not going to replace it here is because if you went to the chemical store to buy ammonium hydroxide, what would you think? You know, I'd like to buy some ammonium hydroxide. And they give you a bottle, and in that bottle is 99% ammonia and water and only 1%, less than 1% ammonium hydroxide. Would you be happy? No, you'd bring it back and you return it and say, you know, where's my ammonium hydroxide? I didn't get my ammonium hydroxide. I got ammonium water. And so they give you a replacement bottle, and the replacement bottle is exactly the same thing as before. And so you go, well, I'm not going to that store anymore. And you go to a different store. And the different store, they give you the exact same thing. And eventually you realize you're never going to get you're never going to get your ammonium hydroxide. I want 99% ammonium hydroxide, 1% ammonia and water. You're never going to get that. Why? Because ammonium hydroxide is unstable. It's going to decompose. This is uphill, but you know, a little bit will form. And so this is why I don't replace it. I just write ammonium hydroxide in parentheses down here. But that's enough, because what's going to happen is it's going to be iron 3 with hydroxide. Well, iron 3 with hydroxide is FeOH3. And ammonium with sulfate. Ammonium with sulfate is NH4. It's just plus 1, so we'll need 2 of those and an SO4. And so these would be iron 3 hydroxide and ammonium sulfate, and then we'll balance everything out later. But first, we have to see if there's a driving force. Now, hydroxides are all insoluble except for group 1 ammonium and calcium, strontium, barium. So this is why hydroxide is so reactive with metal cations. It loves to form precipitates. And so we got a hydroxide precipitate of iron 3. Ammonium salts are all soluble. This is not a gas. And there's no other driving force. There's no stronger to weaker acid. So the driving force is precipitation. And so I write it like this. Okay, if we have driving force there, then I'm going to balance this. If I balance this, then I need how many irons? I have 2 irons here. I only have 1 iron here. So I'm going to multiply this by 2. Now I have 2 irons. And then I have 3 sulfates here. I only have 1 sulfate here. So I'm going to multiply this by 3. Multiplying this by 3 gives me 3 times 2, 6 ammoniums. And so I'll need 6 ammonium hydroxides here. And I have 6 hydroxides, so that works out. So if I need 6 ammonium hydroxides, that means I need 6 ammonias and 6 waters in order to make 6 ammonium hydroxides. And so this would be the CE, the complete equation. And then if we have double replacement, then I'm going to write an IE and an NIE. And so the IE is going to be the iron 3 sulfate. Iron 3 sulfate is a soluble salt. Soluble salts are strong electrolytes. Ionize is strong electrolytes. And so that's going to break up into 2 iron 3 pluses and 3 sulfates. And then ammonia is weak, and weak you just leave alone. So that's 6 ammonias. Water is a non, and so leave that one alone, non-electrolyte. Iron 3 hydroxide is an insoluble salt, so leave that alone. Ammonium sulfate is a soluble salt, so break that up. And that's going to break up into 6 ammoniums plus 3 sulfates. All right, and then we look for the spectators. And so it looks like sulfate is a spectator, and ammonia is not, because on the left we have ammonia, on the right we have ammonium. So it looks like only sulfate is a spectator. And so the NIE is going to be 2 Fe3 plus 6 ammonias plus 6 waters yields 2 FeOH3s plus 6 ammoniums. This would be the NIE here. And the driving force again is just the precipitation, iron 3 hydroxide. Now we have a reaction like this. Then we think, could there be a redox reaction here? Potentially, but could there be a bronzed acid base? Yeah, potentially. But we have a strong driving force for this, so we expect this to happen. If we had some powerful oxidizers, do you see any powerful oxidizers in here? What were the powerful oxidizers? Fluorine, ozone, hydrogen peroxide, permanganate, chlorine, dichromate, etc. I don't see any powerful oxidizers there. Do you see any powerful reducers? What are the powerful reducers? Lithium, potassium. See, here's hydrogen sulfide. Hydrogen sulfide is pretty decent. Sulfides are pretty decent. No. So it's likely there's no redox, nor acid base. So we're good. Okay. So there's a reaction here for number 3. All right, so that's kind of what you do. You start off with I usually start off with looking for metathesis because metathesis typically tend to be the easiest. And then if there's no metathesis, then I'll move on to bronzed acid base. If there's no bronzed acid base, then I move on to redox. Okay. Why don't you try giving these a shot and see how it goes? So I'll let you guys can work together or